said to be thin if gamma has infinite index with G of G, where G is the Zariski closure. Gamma set. So in other words, I will look at all polynomials in the matrix entries which vanish on gamma and look at the set of zeros of that. That is my G. That is G. And I am going to look at integer points here. And one says that a subgroup gamma is thin if gamma has infinite index and its internal Zariski closure. So the motivation for Peter Sarnak for introducing this is what he calls super strong approximation questions and so on. Into this I will not go because that takes too far. The point is that it is not so easy to produce groups which are free. So not easy. Unless they are free products. Again, it's an interesting construction. Into this I will not go. There is a ping pong construction due to states. So, although there are lots of theorems proved about thin groups and their the graphs associated to them, whether they are expanding graphs and so on, but one doesn't have enough examples of thin groups. So, a good way of producing thin groups, at least candidates, are what are called monodromy groups.
Would they be root of unity or not?
I don't yet assume it could be done. For instance, in many of the monodromies which come up in geometry, these are the roots of unity. Okay, so if I want to look at the sort of next level of complication, I want to look at the plane minus 2 points. So the fundamental group here is a free group on 2 generators. But I would like to think of it as the free group on 3 generators modulo one relation. Okay, so a monodromy representation, for example, suppose you have a differential equation like this, the monodromy action will simply mean that we are prescribing 3 matrices, local monodromy at 0, monodromy at 1 and monodromy at infinity, such that the product is 1. So as a representation it's not much, it's just giving ourselves 2 matrices. So there is one particular kind of differential equation which has been studied a lot. This is a differential equation on this space, U. So it's hard to motivate for me, but I'll just write it down. So suppose it depends on parameters, 2n parameters. So I am going to look at this differential operator. So that's my differential operator. And I'm going to view this as a differential operator on P1 minus 3 points. So let us expand this out. The highest coefficient is z to the n, and here it is z to the n plus 1. So it looks like z to the n z. Some polynomial. So that is the differential operator. So if I want to make this monic as here, I have to divide by the highest coefficient. So when I do this, the behavior at infinity and 0 are a bit complicated. These have poles of order n or n minus 1 in these places. But at z equal to 1, it has a pole of order 1 only. So this conforms to this hypothesis. Z equal to 1, z equal to 0 has its coefficient. The coefficients of d equal to 0 have 4 less than equal to 1. So the monodromy matrix H1 looks like this. It's a reflection, complex reflection. So having given you this, let me just give you the result because I don't have much time. So this is a fairly old result of Levent, who computes the monodromy with this data. So let me introduce this function f, the polynomial. Whose roots are exponentials of these parameters alpha I. So there are some assumptions to be made that these two polynomials have no common roots. No common roots. So in other words, alpha j minus beta k cannot be an integer. So we will assume this. So in that case, the monodromy can be computed like this. There exists a basis of the space U such that du equal to 0. This is the d. Such that the monodromy of H1 is this complex reflection. The monodromy at 0 is the companion matrix of F. In other words, it looks like this. Companion matrix. Okay. And the monodromy at infinity is the companion matrix of G. Excuse me. For some reason it is reversed. So, and conversely, given two polynomials which have no common factors, you write the roots as e to the 2 pi I and something. Then you can write down this representation of phi 1 minus these 3 points. It will correspond to the monodromy representation of this root. So it's an if and only if condition. So given this, I can forget entirely about differential equations. Simply look at two companion matrices of f and g and ask when it is discrete, when it's finite, and so on. So that's what I meant by saying, it's purely a question in linear algebra. Given two matrices, how can they generate finite index of group or other? So the first thing to do in this is to compute the Zariski closure of the monodromy, and then ask, when it can be discrete and so on. So that also was done a long time ago. This was really I think it's 89. So I'm going to assume a little bit more about this f and g. So fg is said to be incremental if f is c next to the k and g C next to the k, so if f and g are obtained by smaller degree polynomials decomposing with kth powers, we call them imprimitive. So you don't want to do this because somehow imprimitive case is not so good. So we will take primitive polynomials f and g. Suppose f g primitive. I'm going to, since I don't have much time, I'm going to simplify somewhat ruthlessly. You see, I needed a discrete subgroup in GL and C generated by these two matrices H0 and H infinity. So I will assume that the coefficients of f and g are integral. F, G are integral polynomials. So the matrices that they generate already lie in GL and J. And they have no common factor. This is to assume. And I'm going to assume, coming back to what Ravi asked, that the roots are roots of unity. In other words, the numbers alpha j and beta k are rational numbers. So that's what I'm going to assume. This is not really necessary, but I'll have to introduce extra hypothesis. F, G, the roots of unity, the roots of unity. So with these assumptions, the result is the following. So if I take the Zariski closure of gamma, the connected complement of identity, it's the symplectic group. It's a 0, it's a G0. It's the orthogonal group. If F0 is 1, G0 is 1, so or the other way. So it's sort of surprising that once you demand that the element in the middle is a complex reflection, there is very little choice. you have to have only the symplectic group or the orthogonal group. So this raises the question, when is this gamma inside the integral symplectic group or gamma inside SOQ of Z? When is it a finite index? When is it a finite index? For what parameters? So that is the question. So let me first look at the case SO of the Q. So when I look at the real points, I think nothing is known when SOQ is higher than. So let me assume this. In this case, something is known. Yeah. So if F is there, it's known as squared. So if I look at this here, I get a subgroup of finite index, the monodromy group, the group generated by the two companion matrices, that's gamma. So it's inside SO and minus 1. This is infinite index. Apparently, a fair amount of number theory goes into the proof. This is a result which is not even put on the archive yet. Result of groups. There are some more examples, but I don't have time. And the other is somehow it's of great interest to physicists. I don't know exactly why. This has something to do with Calabi of 3, 4, 6, 1, the monodromy associated to this. So if I take the pair x minus 1 to 4, this is again very recent. So you look at this group is thin. Gamma this time, the value at 0 is 1 and the value of this at 0 is also 1. So we are in the simplest case. And we were in the orthogonal case here. So we are in the symplectic case. It's thin. In fact, it is actually a free product. So, what I want to tell you in the next few minutes is a result which is where the groups are not thin. They are what you can call thick. So this result is Sandeep Singh of Tata Institute University. So suppose I take in the symplectic case that 0 is 1, G0 is 1. And I look at this polynomial f minus g, write it as C times x to the b. So this is the leading coefficient. So the theorem is this. if the leading coefficient is no more than 2, then the group gamma generated to the companion matrices is a finite index. Under all our assumptions, n is automatically even. It's not completely obvious. So, if you assume that f and g are such that the difference leading coefficient not too big, then it's a finite. Okay, so let me just give some examples. There are quite a few examples. So suppose I am looking for primitive pairs of polynomials f g of degree 4. So all the roots are roots of unity and so on. And we are in the symplectic case. Is D4. So the number of such pairs, we just computed this, and there are 112 such examples. Of this, using this criterion, we can show that 60 plus 3 are arithmetic. And this Graf-Thomas technique can yield here that 7, which are of course disjoint from this list, are in. So there are remaining 63%. Remaining 42, I don't know. So for example, here if I replace 4 by 10, instead of 4 I take 10 here, and here also next to the 11 minus 1 by x minus 1, one doesn't know whether it's arithmetic or not. So, how much time do you have?
6 minutes.
Oh, okay, great. So, let me describe the proof in the simplest case, in the case of SP4. So the theorem, the result uses an old criterion due to Boss, Miller and Sayre on generators for arithmetic groups. So let me recall that result. It's sort of better to say it in words. If I have a subgroup of SP4Z, which is Zariski dense, and I want to test whether it's a finite index or not. Generally, if it has lots of unipotent elements, then it's a finite. So that is the criterion. Suppose I have a subgroup gamma of SP4Z, which is Zariski dense, and it has lots of unipotent elements, then it has finite index. So that's what they proved. So more precisely, so I'm going to assume that the symplectic form is lined up like this. So that the intersection of upper triangular matrices of the symplectic group is a Borel subgroup, and intersection of lower triangular matrices of the symplectic group is also a Borel subgroup. So that's the reason. So in SP4Z, I have this unipotent upper triangular matrices and similarly unipotent lower triangular matrices. So here, let me look at this group. U is some stuff here. So all these entries are divisible by n. And similarly here. So if gamma contains so if it has enough unipotent elements, namely the entire unipotent radical of the Borel subgroup up to finite index lies in gamma, and similarly for the lower, this implies gamma is alpha. Okay, so this can be refined quite a bit actually. In fact, suppose I take any higher rank arithmetic group which is non-Bohr compact, therefore there are enough unipotent elements, and gamma is Zariski dense in GZ, which contains a finite index subgroup for the upper triangular matrices and the lower triangular matrices, then it's a finite index. So this is also true, but we are not going to use that things in that generality, only this part. So I won't sketch a proof of such things, but this is fairly easy to show that gamma for Z is Zariski dense. And gamma contains a finite index subgroup, not of the full upper triangular matrices, but only this part. It is a unipotent radical of a parabolic subgroup. This parabolic. This implies gamma finite. It's not difficult to show this from here. It's easy algebra. Okay, so we want to get into such a situation that the monodromy group contains the unipotent radical of such a parabolic, this parabolic. And that's what we will do. So you see, I have these two companion matrices, let me recall them. I had two polynomials f and g such that the difference had leading coefficients at most 2, and this was a companion matrix. So if I take the inverse, A inverse B, I call this C, this has the property that its identity on a three-dimensional subspace, because A and B coincide on their companion matrices. On the first three basis vectors they coincide, and because we are in a symplectic group, it looks like this. So I have one unipotent element. So I can take three unipotent elements: C, A inverse C, A to the minus C, A squared. So I have these three unipotent elements in the monodromy, which I know is Zariski dense by the Boyka's theorem. Now each one of them has a fixed space of dimension 3. So the three together has a fixed vector. So these fixed vector B in Q4. So this vector is fixed, and therefore the orthogonal complement with respect to the symplectic form is also fixed. So this flank is fixed. Flank is fixed by these three matrices. So if I choose a good enough basis, it turns out that I can assume that the matrices look like this. But the third one will no longer be integral. If I choose change basis like this, the third one will be a rational unipotent matrix. Yeah, so here comes the final point. If C is less than or equal to 2, the group generated by these two matrices 1C01 and 10C1 is a finite index. It's an arithmetic group. And I have a unipotent rational matrix. So if I take a large enough power of the unipotent element, it lies in this subgroup. So there is a word in these three elements, C, A inverse C, A, and this. There is some word which has lost this part. So that word looks like 1. So this is an element of our parabolic subgroup. And by taking conjugates with this C and this one, we get all of the parabolic. So that completes. Thank you for that.
Are there any questions? Yes.
What can one say about limit sets of these groups?
They're lattices, so limit sets are limit sets of lattices. It's a finite index.
No.
Yeah, but in the other case, I don't know. In the Sarnac case or so, I don't know. I think they're pretty large.
But are they full or they can be smaller than the geometrical?
I don't know. I'm not looked at it, but of course, here, once it finite index will be.
No.
Any more questions? Okay, so let's thank our speakers again.
I was waiting for it.